Okay, so we've been talking about injective linear transformations, and there's this other notion of surjective linear transformations. If you know about properties of functions, that's the same thing as onto. And we'll see this later, but if I draw a simple cartoon of this type of linear transformation, what it means is that every point here is hit by at least something. Now it's possible that two points map to the same point, but it's necessary that every point out here is mapped to. If there's a point here, there is a point here that maps to it. And that's reflected in this definition. If you have a linear transformation, it's surjective if for every v and v, this is my v and this is u, but for every v and v there exists a u such that t of u is equal to v. So any v here has a u associated with it. All right, for instance, he gives an example of a non-surjective function. If you have the function x squared, you can't map x squared onto minus 3, at least if you're mapping the real numbers. Okay, so the x squared is not a surjective function from the reals to the reals. Okay, so that's that. So here he relates surjective also to onto. So here, let's see. Here's a case of a linear transformation that's not surjective. Here it's defined like this, and we know that we can relate this to a matrix. So you want to, he will show that in fact this element v, which is in the codomain, is not in the range of t. Now if it was, that means I could set minus 1 equal to this. I could set 2 equal to this. I could set 3 equal to the third one, 4 minus 1 equal to the fourth one, and 4 equal to the fifth one, and find a solution. But he's going to show that in fact there's no solution to this vector equal to this matrix times this. And we've seen things like this before. We know that if we row reduce and if we row reduce the augmented matrix and get a pivot entry in the last column, we know that it's not possible to find a solution to this system. Okay, right. So here he says he just chose V. He had some magic way of choosing it. He's just showing the notion of surjective. And here we have this is non-surjective. Non-surjective means there are singletons out here. Okay. To show a linear transformation is non-surjective, it's enough to find a single element that is not mapped. All right, so let's see if we can show that something is surjective. All right, to show something is surjective, we need to show that in fact every element in the codomain can be expressed in such fashion. Okay. Right. So that means we should be able to, for no matter what v we have here, there should be some set of u that works. Okay. All right, now it turns out in this case, this matrix, this coefficient matrix, is actually non-singular. If the coefficient matrix is non-singular, then let me call this coefficient matrix A. I'll call this coefficient matrix A. What this is saying is AU is equal to V. Okay. Now, if A inverse exists, I can multiply both sides by A inverse, and that means that U equals A inverse V. So what does that mean? That means that no matter what V I have in the codomain, if I multiply it by A inverse, I can find a U that maps to it. Okay, so non-singular matrices correspond to surjective linear transformations. Non-singular matrices gives a surjective linear transformation. Now we also saw that non-singular matrices give an injective linear transformation, so that tells you there's something very special about non-singular matrices. Okay, remember, non-singular matrix has to be square. All right, so here's the cartoon for surjective. There's nothing over here that's not hit. Another example of a surjective linear transformation, right? Now, you really can sort of consider this as mapping column vectors to column vectors. You can see this is four-dimensional, and this here is also four-dimensional. And you want to show that any 2 by 2 matrix can be obtained as T of some polynomial. Okay. So you want to be able to find any output here that is the result of some input here. So here you're showing XYZW is equal to T of this. It's a little bit unfortunate because the X here does not mean the same thing as the X here. The X here is a constant, and the X here is the variable for the polynomials. Now, this X has to do with entries of the matrix. This X is just the variable in the polynomial. So that's a little unfortunate that he did that. Now we know that if we have this polynomial ABCD, it maps to this matrix. That's the definition of my T. T maps ABCD into a matrix like this. So we need to set A plus B equals X, A minus 2C equals Y, D is equal to Z, B minus D is equal to W, and see if for no matter what X, Y, Z, W, can we find ABCD that works. All right, so here's the system. Here's the matrix. Matrix is non-singular, therefore it has an inverse. We do the very same thing. Compute the inverse, multiply both sides, and we get the coefficients of the polynomial can be obtained for no matter what matrix entries we have. Okay, and here you can actually check that if you put this combination in for ABCD and take the linear transformation of that, you get the vector, the matrix XYZW. All right, well, let's talk about range. Now, range, we talk about ranges of functions intuitively. If we go back to this picture here, if I was going to take this linear transformation, the range is the set of all elements over here that are hit by at least one vector through the linear transformation. So, for instance, these, oops, let's get rid of that. Okay, these two vectors are not in the range. To be in the range, it must be on the receiving end of some vector through the linear transformation. So in other words, if this is some v, then there must be a u that maps to v. So in fact, if I take the set T of u all maps into this set here. So in fact, the range of T is the set of all vectors of the form T of u. So here's the definition. The range of a linear transformation is the set of images of all vectors u in u. That corresponds to the picture I just showed. Take any vector in u, take its image under T, and that gives me all the vectors in the range. Let's look at an example. Here we have a transformation from C3 to C5 given by this rule. You can check that that's linear. Now, if we wanted to take T of an arbitrary vector u, which is what determines the range, we can replace the x's with u's. If we do some rewriting, we find out that, in fact, T of u is a linear combination of these three vectors. In fact, that means that T of u is contained in the span of these three vectors. Now, it turns out that these three vectors are not linearly independent, they're linearly dependent. Using methods that we've seen before, you can find a basis for these. If you remember, we can turn these column vectors into row vectors and then row reduce, and that will give us a basis. So these two vectors form a basis of this range, and we can see that the range is a two-dimensional vector space. Okay. And that's actually the content of the next theorem, that the range of T is always a subspace. And the way you can show that is that the range of T can be expressed as a span. And we know that the span of a set of vectors is always a vector space. Now that's one way to do it. Another way, he actually shows this directly, that the range is closed under the additive operations. That if we have two elements in the range, then in fact the sum is in the range. And if we have an element in the range, then the scalar multiple is in the range. So range of a linear transformation is always a subspace. All right, so let's consider another linear transformation where you take C5 to C3. You're going from a bigger vector space to a smaller one. And if we write T applied to an arbitrary vector, U1, U2, 3, U1, U2, U3, U4, U5, in the same way you can show that V will be a linear combination of a set of vectors. And we can show that this set of vectors in fact spans all of C3. Right? And when we do the reduction, to change these to row vectors, row reduce, and you'll get the identity. Okay? All right, now let's relate this to surjective. Suppose we have a linear transformation that's surjective. Well, it's surjective if, and only if, the range is equal to the codomain. This is the same thing with functions. If you've seen this in your discrete math class, that function is surjective or onto if and only if its range is equal to its codomain. And you can show this by, to show if and only if, you show that if it's surjective, then the range is the codomain. If it's surjective, then for any v, we can find T of u is equal to v. So that means that the range must include all of the vectors in the codomain. On the other hand, if the range includes the codomain for any v, we can find a u such that T of u is equal to v. So this is a very simple proof. Let's look at another case which is non-surjective. Okay. The way to construct something that's non-surjective is to find a linear transformation whose range vectors doesn't span the entire space, and then choose another vector that's not in there. So how do you choose a vector that's not in the span of a set of vectors? How can I find a vector that's not in the span of these four vectors? Well, let's take a linear combination of these four. -1 times the first, plus 2 times the second, plus 3 times the third, plus -1 times the fourth. That specifies the 1, 2, 3, 4 first components uniquely. And it turns out that that means that the only way to make that happen is for the last component to be -8. So if I just change the last component to be anything other than -8, I'm going to have a vector that's not in the span of these four vectors. Let me do another example. Suppose I take the vector 1, 1, 1. Okay? If I take the vector 1, 1, 1, to make that a linear combination, or 1, 1, 1, I think I need a fourth one, 1, 1, 1, 1. And then this one is not yet decided. If this 1, 1, 1, 1 undecided is going to be a linear combination of these, I would have to take 1 times this, plus 1 times this, plus 1 times the third, plus 1 times the fourth. Right. What does that mean the fourth component would be? Well, the fourth component would then have to be 1 minus 1 gives me 0, minus 1 gives me -1, plus 2 gives me 1. So I know that 1, 1, 1, 1 is in the range. But 1, 1, 1, 1, 0 is not in the range because it can't possibly be a linear combination of these four vectors. Okay, more examples, and let me stop there.